Welcome. So, we were discussing about the equivalent circuit of an induction motor. See, initially we just told about how torque is produced in a motor and tried to understand it physically what is happening, that is the rotor field, stator field, this that, and the interaction of the stator, resultant field and rotor field gives you the torque. Now, we have gone further and we tried to develop the equivalent circuit of a 3-phase induction motor per phase basis, and from that looking at the power flow that takes place in the machine starting from supply source to the mechanical power developed by the motor. So, we developed this equivalent circuit and told you that this is the equivalent circuit, which is stator resistance, stator leakage reactance per phase. Now, it is similar to that of a transformer, and then you have this magnetizing branch, which is JXM. I mean all reactances are J, that is there, and then on this side the reflected rotor parameters came out to be x 2 dashed, and this is R 2 dashed by S. Okay. And slip depends upon the operating point of the induction motors, and slip is a measure of speed as well, because you know actual rotor speed, all speed are mechanical here, is 1 minus S into N S. So, and N S is the synchronous speed. So, now this is the per phase applied voltage V 1, and this is the thing. Then what I did between these 2 points, we found out the Thevenin's equivalent, and this circuit was redrawn as R Thevenin's, X Thevenin's in series, and then this remains V 1, and then X M goes, and you are having this equivalent circuit. Okay. And this current is suppose I 2 dashed. Then we just considered the power balance. After we have got the equivalent circuit, the rest of the work is somewhat routine network type analysis. No field is coming here, that is one good thing. So, the input power to this circuit is and I drew this I will not waste time. Last time we told you that this equivalent circuit means you are giving some input power drawn from the supply, out of which a portion will be lost in the stator coils as stator copper loss 3 I 2 square R Thevenin's, that's value will be I 2 dash squared R Thevenin's. Then rest of the power is as if crossing the air gap and entering into the rotor. That is why it is called air gap power, for our own understanding. Okay, we will interpret it like this: total input power minus this stator copper loss or stator loss, whatever is there. There will be core loss also, that we will take care later, PAG, and then this power after entering into the rotor circuit, there will be a power loss in the rotor resistance, which mind you is 3 I 2 dash squared R 2, which is same as 3 I 2 square R 2, because we have referred everything to there. Okay. Now, recall that this equivalent circuit, the power involved in this circuit is the air gap power, because this is the power, real power entered. So, PAG PAG is 3 I2 dash squared R2 dashed by S, and obviously rotor copper loss is equal to 3 I2 dash squared R2 dashed. So, it looks like rotor copper loss is nothing but S into PAG. Now, so from PAG, if you subtract this rotor copper loss, if you subtract it, then you get P gross mechanical, which will be equal to PAG minus P rotor copper loss. If you subtract, this becomes 1 minus S into PAG, and this is shown in this one. PAG comes, then you subtract rotor copper loss, then you get P gross mechanical power, whatever mechanical power. It is called gross because a portion of it will be lost to supply the mechanical losses in friction, etc. This is not the net mechanical power output, but gross mechanical power output, because this gross mechanical power output only decides what is the total opposing torque developed by the machine put on the shaft of the machine, including the actual mechanical load torque and the frictional power. Anyway, so this is the thing. Now, our target is to find out what will be the torque developed by the machine. So, this we will do in this way. I have got the P gross mechanical power, from which I will find out what is the mechanical torque present on the shaft of the machine, and we will assume that the machine is running with a fixed value of slip S, that means at a fixed RPM. Therefore, if I can estimate the mechanical torque, then the electric torque developed by the machine must be same. So, remember this visual picture, any motor, this is the electromagnetic torque, this is the direction of rotation Nr, and the gross opposing torque T mechanical gross. These two must be same, so that it is running with a particular RPM Nr or with a particular slip, because every Nr has got a, if you map it to slip, it has got a unique value of slip. So, that is the thing. Therefore, from this I will say, and then I told one very important relationship, that is this must be remembered, that is PAG is to P rotor copper loss is to P gross mechanical is in the ratio 1 is to S is to 1 minus S, that we have found out. So, this is the thing, P gross mechanical. Therefore, total opposing torque which is sum of the frictional torque to be overcome, frictional torque plus the actual net mechanical torque, which is doing useful mechanical work for me, that is the thing. Therefore, this must be equal to 1 minus S into PAG, that is P gross mechanical, divided by 2 pi Nr, where Nr is the actual rotor speed, actual mechanical I will repeatedly not write, but anyway actual mechanical speed Nr in RPS. if you want to get torque. So, this is the thing. Now, what I will do is this, for NR I will substitute this thing here. So, it is like this, then 1 minus S into PAG divided by 2 pi 1 minus S into NS, and then you see 1 minus S goes and gross mechanical power developed will be equal to 2 pi NS, and this must be equal to the electromagnetic torque developed, because machine is running at a constant speed or constant value of slip. So, we are trying to get an expression for electromagnetic torque not in terms of delta or BR or BS, but in terms of equivalent circuit parameters. That is the idea here, because these equivalent circuit parameters, if these are known to me, then I will be able to calculate torque simply by using the equivalent circuit parameter. So, this is the also equal to electromagnetic torque developed by the machine. At slip S. That is the thing. So, this is the expression of electromagnetic torque, of which you must note this point, that this Ns is constant. Ns is equal to 2f by p is constant, so long the supply frequency is constant and machine is given. So, p is also constant. Therefore, the electromagnetic torque developed by the machine, if you divide by 2 pi ns, the air gap power, then its unit will be in Newton, so much Newton, if this is in watt and this is in RPS. Now, note that to calculate the electromagnetic torque, therefore, if you have estimated the air gap power, that itself is a measure of electromagnetic torque developed by the machine. Why? Because 2 pi ns is constant. So, if you have calculated PAG, electromagnetic torque is as such calculated. I have to simply divide by a constant number 2 pi ns. So, sometimes PAG is considered to be the torque developed, and PAG alone its unit is watt. So, it is called given a name synchronous watt. So, PAG is also T expressed in synchronous watt. This is a term, synchronous watt. So, sometimes torque is expressed in Newton, then so torque T is equal to PAG, you can write absolutely correct, but write synchronous watt, its unit is, or you write PAG by 2 pi ns, and this will be in Newton meter. That is the thing, should just recall. Now, after I have learned that torque in Newton meter is this, let us further simplify this expression, that is T PAG. PAG is nothing but 3 I2 dash squared R2 dashed by S by 2 pi ns. Now, I want to express this expression of the electromagnetic torque developed by the machine in terms of equivalent circuit parameter. and equivalent circuit is this, which we will consider the Thevenin's equivalent, this circuit. So, this I2 dashed is nothing but V Thevenin's divided by square root of R Thevenin's plus R2 dashed by S whole square plus x1 plus x2 dashed x Thevenin's plus x2 dashed whole square. This is, so I have to put this value here, and if you do that you will get 3 V Thevenin squared by 2 pi n s, square it, and in the numerator you have R2 dashed by S divided by, in the denominator it will be, these are algebraic manipulation, R2 dashed by S whole squared plus x Thevenin's plus x2 dashed whole square. So, this is the expression of the torque in terms of equivalent circuit parameter. So, if somebody says machine is running steadily with a slip s equal to 0.05 and suppose the all the parameter values of unknown, and I will just put those that value of slip and tell okay, if the machine has to run at this slip as a motor, then the electromagnetic torque will be so much of Newton meter. So, by putting different values of slip, I will be able to calculate how much torque the machine is capable of developing. That is, I can make a table here, I will write slip, and value of the slip range is known, and therefore, by putting different values of slip varies from 0 to 1. So, if you can easily see, if you put s equal to 0, this torque will be approaching 0, because R2 dashed by S is there, this will be, if S tends to 0, torque will be 0, tend to 0, because there is a square term here, R2 dashed by whole square, this will dominate, others are negligible, and on the top also there is R2 dashed by S. So, ultimately the denominator becomes infinitely large, I mean just telling mathematically. So, torque will be 0, physically I know why the torque will be 0, because if slip equal to 0 means n r equal to n s, and machine cannot develop any torque. Similarly, I will put say s equal to 0.01 and I will get some number, I will put it here like that 0.02 and so on, and go up to s equal to 1. So, all these entries I can make, provided I know the equivalent circuit parameters. Suppose these are given to me. So, I will be able to calculate, make a table where y axis will be torque and slip is varied from 0 to 1. So, this I can make a table like this, and after that what I can do is this, I can plot this for a given machine, and suppose this is slip equal to 0 and this is slip equal to 1, this axis is slip. And when you are plotting this slip this way, I know this is speed, one and the same way, either you tell the speed, and this is n r equal to 0 and this is n r equal to n s. You must keep this picture in mind. Now, if you sketch this tabulated value of torque against slip, which I got from this expression, the typical curve will be somewhat like this. the slip varies between 0 to 1 for motoring mode, and the characteristics, typical characteristics will be like this. Understood? This is the shape this curve gives you, and you will note that once this torque slip characteristics, this is called torque slip characteristics, torque versus slip characteristics. And if you get this torque, you will note that there is a slip at which the torque increases as slip value increases, then it attains some maximum value T max at some slip, say s equal to alpha. At s equal to alpha, there is a maximum value of the torque, and then torque once again decreases, and this is a typical torque slip characteristics, typical characteristics. And also for a well designed induction motor, the value of the slip at which the machine is capable to develop maximum torque, its value typically will be about, if this is 0 to 1, this will be 1/10 of this, about it is no fixed number. I am telling you the expected value of the slip for which the torque attains maximum is about, alpha value will be about 0.1. So, this of course, is 1/10 of this one, indicating that the curve go to maximum at a very small value of slip, then it decreases and this comes here. And this is the value of the obviously starting torque, T starting of the induction motor, because s equal to 1. As you switch on the supply to the stator, s equal to 1, machine is capable of developing this much of starting torque. Obviously, frictional torque, if it is opposing torque is less than this, then machine will accelerate. If the opposing torque present is this much, machine will not start, because starting torque will never be able to match this opposing torque, and it will remain stationary, blocked condition. Although the induction motor has got a starting torque, definite starting torque, T starting, but it must overcome whatever opposing frictional torque is there, so that it accelerates. Okay. So, this is the typical torque slip characteristics. Then the next question comes in, okay, in terms of equivalent circuit parameters, can we tell what will be the value of T max and at what slip that T max occurs. So, at what slip T E max occurs, and what is the value of T max? Can we derive some formula? What is the value of T max? At what slip? That slip I have identified as alpha. So, to do this, what should I do? So, we write down the general expression for T, that is T is equal to 3 V Thevenin square, it is to be written actually, rewritten 2 pi n s R2 dashed by S divided by, this is the general expression of the torque, R Thevenins plus R2 dashed by S whole square plus x Thevenin's plus x 2 dashed whole square. This is the general expression of the torque, of which the equivalent circuit parameters are constant. V Thevenin's is depends on primarily applied voltage and small r 1 x 1. So, all things are constant except S, and I want to find out at what slip T E max occurs. So, it comes to our mind that then what we have to do is this, we have to calculate d T E d S. You differentiate this, equate it to 0, and from that and try to get the value of alpha. Alpha is the slip at which maximum torque occurs, but it looks like it will be slightly involved task. So, we will not calculate it in that way, rather we will try to get that expression in a much elegant way, because I know the equivalent circuit of this induction motor looks like this. This is R Thevenin's, this is X Thevenin's, and this is your magnetizing inductance JXM, and this is x 2 dashed, and this is R 2 dashed by S, and sometimes people put some variable resistance sign to indicate that machine may operate at different slip. So, it is only this parameter which goes on changing as you change the degree of loading of the machine, and this is your per phase applied voltage. So, with this equivalent circuit, the value of the slip, that is S equal to alpha, we are looking for, which will give you the maximum torque developed, can be very nicely obtained, and this we will continue in the next class. Thank you.